we're going to start is we're going to start by talking about potential outcomes and directed acyclic graphs. More generally, we're going to talk about just kind of the structure for how we're going to think about causal effects and more generally treatment effects. So if you haven't heard of these things, that's sort of what we're going to go over now. Conceptually, we're really interested in causality. So not every research paper you're going to write or that I've ever written is about causality or is about a causal quantity rather. If you're estimating some descriptive statistic, you're interested in maybe measuring some kind of characteristic. These may not be causal measures. You're not always estimating, what is the treatment effect of X on Y. But almost always the implication or takeaway of a paper is something causal, right? So, if you think about wanting to do a topic, like if you present, for example, a gender difference in some outcome. So you do an empirical exercise where it's a descriptive characteristic where we're documenting differences, wage gap difference between men and women. Now, that is not necessarily inherently causal. So for example, a paper I've done is I sort of document the gender difference in representation of women in the profession of economics. We don't have a deep number of causal parameters that we're trying to do in that paper. It's mainly descriptive. But obviously, at the heart of the exercise, we're interested in something causal, which is like, what is causing this discrepancy or this difference in men and women across topics and across different things? So, regardless of what you're doing in there, you typically want to say something causal. And so what we're going to be doing today is kind of talk about different tools that are used to discuss causal questions. I'm really going to be trying to emphasize a multimodal approach. So there's a number of different ways that economists, so Yale kind of famously has a different structure for doing this than a lot of other places. If any of you interact with Phil Hale, he'll have very strong opinions about how to do this. We're going to talk about basically 3 different modes of doing and talking about causal questions in empirical research. And really what I'm trying to do is set terminology and definitions for future papers when we're talking about how they work so that we're kind of have a familiarity for it. So one thing I want to mention, so there's this Aristotle quote where, causality, kind of thinking about causality goes back, and the causes of things goes back, thousands of years. People have been worrying about this for a long time. The true underpinning of how you think about causality, it's pretty philosophical in nature. Basically, the summary for this class is if Aristotle wasn't able to settle the question, then we're not going to in the 21st century either. And so as a consequence, I'm not really going to delve into them too much. There's some really, I think, deep and interesting questions. There are 1 or 2 settings where I'm going to kind of really push, and we'll talk about this on Thursday, push certain ideas that I think are important and valuable for economists to have in mind. But for the most part, these are tools, and you can have your own very strong opinion about how they should work generally. The key point that I want you to say or keep in mind is that economics research is messy. So being clear in causality really helps you articulate your assumptions. So by forcing ourselves to say, look, we're thinking about the effect of X on Y and we're doing it in this way, a lot of times this makes us realize what are things that we need to be true that we wouldn't have thought of otherwise. The second thing that I do want to highlight, though, is this is a little bit implicit, but economics kind of has its own language for talking about things, and we're gonna come back to this later. But there are different terms in language that you've learned by doing theory, by your own econometric classes that make it so that economists who read what you're doing are going to understand things very differently than statisticians or political scientists or marketing or whatever potential field that you work in. So really what you want to grasp is what is the underlying framework of what you're saying and what kind of assumptions do you need and how can you potentially translate that? I want to teach you terminology, but I also don't want you to be so hung up on the terminology that you don't understand what's going on. So this is a little bit why I'm going to try and describe several ways of understanding the same question. If this sounds vague, hopefully it won't be by the end of class. But the idea is that you should not have to say, oh, well, I'm just making conditional independence assumption. And it's like, okay, well, what does that mean? I'm making a conditional independence assumption. You should be able to articulate what that means in a very clear way. Any questions so far? No. Okay. You can raise your hand or you can just jump in if you've got questions. Okay. So in a lot of the ways that I'm going to talk about things in class today, I'm going to kind of refer to this type of example. This is obviously very apropos, but imagine some sort of binary outcome where we're thinking about whether or not someone is immune to COVID, and the treatment, D, is whether or not someone gets a vaccine. And so obviously our question, as you know, we all want to know is like, does D cause Y? And we're not even thinking about data right now. So we don't have a data set. We haven't done anything. We just want to understand how can we know, what can we know about what's knowable? And so what I'm going to first talk about is the fundamental problem of causal inference, is that one way of viewing this question is to say, look, for any given individual, we can only observe one world. Either it's a world where they get the vaccine or it's one where they don't. So this is a very famous line. This fundamental problem of causal inference is to basically define a treatment, an outcome. So yi is the outcome for a person I coming from a population of n individuals, where there's basically two worlds, two potential worlds. So Brett, there's two potential versions of him. One is a world in which they receive the vaccine. One is a world in which they do not. We can't see both worlds. And so this notation, this way of basically implying that there are two counterfactual worlds for Brett, that it's a function of was there an intervention or not. This is referred to as basically as the Neyman-Reuben causal model, or the Reuben causal model. And this kind of idea of defining things in terms of their potential outcomes is one key way in which people think about causal outcomes. The key assumption here in terms of thinking about this for now is that we're going to be assuming that Brett's outcome is only affected, sorry, Brett, you're now the running example in this, is only affected by his own treatment. So this is called the stable, it's one of two pieces to what's called the stable unit treatment variable assignment. And so conceptually, what that gets us is the idea that yi, which is Brett's outcome, is this function at the top. So it's yi equals di, yi1 plus 1 minus di, yi0. So you can see here, right, that it's just this true outcome is a function of, well, if di is on, then we see yi1. If di is off, then we see yi0. And what that gives us is, well, there's two worlds. There's the world in which Brett is treated. There's the world where Brett is not treated. We only observe one of them. We can see whether or not they're treated, and that gives us different outcomes. I again want to just emphasize this SEPHA thing as not being non-trivial, in the sense that, you know, there are many worlds in which it could make a lot of sense that, like, if Aslihan was treated, that would have an impact on Brett in many other circumstances. Think a wage training program, right? Where if we start treating a lot of people, then all of a sudden my wages might be affected by other people's treatments through, for example, the labor market. If there's some aspect to which a budget constraint causes treatments to affect one another, that becomes a lot more complicated. Or you think about a village where there's information that spills over, things like that. So this is a crucial assumption, but is one that could be easily violated. Conceptually, in the potential outcomes framework, causal inference and missing data are really tightly linked. So any causal answer basically uses assumptions to infer the missing counterfactual. So why is that the case? Well, if I'm thinking about, I want to think about the effect of D, this treatment, well, what I need to do is be able to compare people who got the treatment and didn't get the treatment. Well, in a lot of cases, I can't see it for the same person. And so I need to have a counterfactual for that person. And so using different statistical methods, we're going to potentially try and infer what a counterfactual is. So Brett, we see that he gets the treatment, we see some outcome, and then we say, all right, well, what's the right comparison group for him or all the other people who got the treatment? And so almost every problem that we look at is going to be a statistical approach for trying to generate a counterfactual, be it through linear regression, be it through propensity score matching, etc. These are all approaches for trying to generate a missing counterfactual and effectively deal with a missing data problem. Before we kind of talk about all the potential estimands that we're interested in, it's very useful in your own mind to think about, what is the goal of your statistical approach? So, if you think about this from the process of a research paper, it depends kind of on what you're doing, right? Sometimes your research goal is to estimate a structural parameter. You may, for example, be interested in a tax elasticity or an investment elasticity with respect to taxes. You might be trying to understand a policy intervention. You saw a policy intervention you did one in India. There was some sort of treatment that was done, and we're trying to understand what the impact of that was on different markets. It's useful to kind of understand what your goal is, because that's going to define the type of approach that you're going to do. When you're doing something that's more structural, it's very challenging to back out a structural parameter without putting a lot more structure on the problem. Whereas a policy evaluation, you can do the kind of internally valid policy evaluation, and then think about how can you extrapolate that to other settings. Very quickly, let me kind of do an aside here. This may or may not be something that you understood or knew super well. I feel like this is a terminology thing that is just assumed of the reader. I want to kind of make sure that everyone understands what kind of the difference is between these three things. So an estimand is typically the quantity that you want to estimate. It's the thing to be estimated. It's a causal term that you want to know, be it the average effect of a treatment on something, the structural elasticity, et cetera. That's the estimand, and it's the target parameter that is kind of unknowable, quote unquote. The estimate is the approximation of the estimand that uses some finite data sample. So you have some data draw from the population. You're going to get an estimate, which is going to somehow try and approximate the estimand. And then the estimator is the method or formula for arriving at the estimate for an estimand. So in the appropriate way of humiliating myself in front of the first day of class, I'll show you guys the song I wrote about this. And then we can get back into doing this seriously. 1 second, I have to find it. Here we go. Oh, no, hold on, I have to show the sound. Think of this as like the break. The estimand is what you say when you are asking a question. The estimand should always be defined. This is no suggestion. The estimand can be a simple thing like the mean of a population. The crucial thing about an estimand is it's defined pre-observation. So if you came along and you took some data, you plugged it right into Stata, then you wouldn't have an estimand. There we go. That's great. So now there's no excuse. If anyone ever gets that wrong, no excuse. I humiliated myself for you guys. But in seriousness, the thing that actually is true about this is what happens a lot. Thank you, Brett. What happens a lot in papers thinking about these types of approaches is people are a little bit vague on what they mean by what they're trying to estimate. So I think, and you can estimating more than one thing. You could have more than one estimand in mind. But by doing that, by sort of concretely being like, look, this is what I'm trying to do, it will very clearly help you understand what is knowable and what's not. And is that something that's knowable, or what additional assumptions do you need to know for that? So the reason I say this, let's give an example of what I mean by potential causal estimands, right? So these are kind of three very simple examples that show up in the treatment effects literature. The simplest is what you'd call the average treatment effect. So here, TI is, did I define TI before? Or maybe I didn't. So TI here is tau I, Tau I, consider that to be the individual treatment effect, which is not knowable. So Brett's tau I is never observable in the data. He would love to know that, because that, if every person knew kind of their own individual treatment effect, that would help them make a decision about whether or not it would be worthwhile. It's not, because of the fundamental problem of causal inference, that's not knowable. But what we could talk about instead is the average treatment effect, which is the average difference between these two. So in expectation, what is tau I? Now, the reason it's called the average treatment effect and there's these other ones is that this is defined over the whole population. All right, so all people in the data set or in the population, what's this treatment effect? Versus, you could think about it as the average treatment effect on the treated. So the reason why this matters is that, you know, if you think about the effect of a policy and you want to sort of do a retrospective and think about what the impact was, the average treatment effect on the treated is going to be the treatment effect for just those who received the treatment. Now, that's going to sort of subset on a subset of people. And the only piece that you really don't know is what is their counterfactual, right? So if we think about this here, this is kind of the crucial piece of it. Is if we take the average treatment effect on the treated, well, that's tau I conditional on di equals 1. So that's, they got the treatment. Well, there's these two pieces that, thanks to the linearity of expectations, they kind of separate out. Well, this first piece is totally knowable, right? We just take the average of all the people who got the treatment. That's great. What we don't know is this piece, which is the expectation of yi for the, given that they didn't get the treatment, conditional on getting the treatment. Well, by definition, we don't observe these folks. And so the question becomes, how do I infer that piece in there? In this other version, obviously, this kind of shows up in both ways. And then, you know, another version, another estimand that you might be interested in is some conditional average treatment effect, where you're interested in tau I, but for some subpopulation. So you could be interested in gender differences, you could be interested in employment differences, size differences, et cetera. Xi is some additional characteristic. Any questions so far? These, I think you probably have seen a version of these before. So these are potential versions of estimands that you could be interested in. And it's helpful. These are, you know, these are ones that you can throw offhand as being very simple things that you're interested in. Well, the reason why it's useful to define the estimand, and this is what we're about to do, is it lets, the case that I was making is that defining the estimand helps you understand what is knowable and what's not. And conceptually, this is effectively what we would call identification. What's identified? So this is something that people have many strong feelings on for a number of reasons. So we're going to focus on right now, definitionally, on what like that identification means from the purely, what's the right word? Dictionary perspective of it. When you say something is identified, it means in particular that it means that in a world with no uncertainty about the data, can we always identify the value of tau, so tau 8, for example, from the data we observe. And in other words, what this means is it's an invertibility condition. It's the idea that we can invert the parameter of interest back out from the data that we observe in basically in the wild. That variation in the data set will help us identify the parameter itself. Now, why am I belaboring this point so much? Well, so Arthur Lubel has this paper so it's in the syllabus that is called Identification Zoo, where it's basically one long paper complaining about all the ways that the term identification is abused by empirical people, which is totally fair. And really, econometric identification means one thing. It means that you can identify parameters uniquely from an observable population that is generated in the data. So why does that matter and who cares? Well, the reason it could matter is that you want to know when something that you're interested in, namely the S demand, is knowable from the data, right? So if you say, I want to know the effect of X on Y or D on Y, if it's not identified, you're already kind of doing something that is implausible. You're approaching the wrong question. Some questions, the answers are not necessarily knowable. And by forcing yourself to say the thing that my causal S demand is blah, that's going to really help you identify exactly this point. So, why would something not be identified? Well, consider the following. So remember that average treatment effect on the treated that we were talking about. So tau ATT, this could really be true for any of those average treatment effects that we were just discussing. This first piece, we were talking about this expectation of yi1 conditional on di is identified mechanically. Just that's a thing we know we observe because when di is on, we can take the mean of it. It's sort of, we observe it in the sample. Well, what happens? How do we know expectation of yi0 conditional on di equals 1? Well, more generally, to be able to estimate that, we need an assumption about the relationship between di and yi0 and yi1, right? So what I'm building up to, and I think anyone because you're all familiar with empirical work and thinking about causality intuitively, is that I've put no structure on the relationship between yi and di. And so there's no random assignment of treatment or anything like that. So it's not obvious you could inherently identify this parameter, specifically this tau ATT, without additional assumptions. So the first assumption we're kind of learn that really is the term most relevant for thinking about treatment effects is this idea of strong ignorability. This is basically the condition under which the average treatment effect is identified. Strong ignorability is, and so this conditional statement is really just there so that we can do the conditional average treatment effects as well. But basically the theorem is if di is strongly ignorable conditional on a vector xi if the pair of yi's, the observed, these two unobservable terms, so the one where you're treated and untreated, if these are conditionally independent of di, conditional on xi. So what does that mean? Conceptually, it's the idea that when I treat you, if I treat Erin, I'm not giving her the treatment because she has a good outcome, and I'm not giving Natalia the treatment because she's going to have a bad outcome of it. Then I'm not sorting my treatment in such a way, because what I need to do is I need to be able to use their outcomes to generate counterfactuals. And so by having these be independent, I'm going to be able to generate counterfactuals just by taking the averages within those who received it and those who didn't. The second term, the strong ignorability, I don't want to say it's philosophical because it's not. It's obviously necessary, but it's to say that there exists an epsilon greater than 0 such that the probability that you get the treatment conditional on your xi is basically bounded away from 0 and 1. So it's greater than epsilon and greater than 1 minus epsilon. This should just be 1 minus epsilon, not epsilon I. So what is that saying? That's just saying that all of you have the chance of potentially getting the treatment. It's not all, the problem is that if you don't have that, then you basically wouldn't be able to identify one of the pieces because there would be groups where you would have no treatment at all. And so you would never be able to generate that counterfactual group, or you'd have somebody who never got the control group, for example. So it's basically asserting that there's both treated and untreated individuals. This term strong ignorability is very common in the stats and political science literature. It is effectively what you have in mind if you're, for the economists in the audience, when you say something is exogenous, this is kind of what you have in mind. It's not very, I have to say that I think exogenous is not very precise, and this is a very precise statement specifically about conditional independence and treatment. If you were trying to be clear, what you might say instead is, DI is conditionally randomly assigned, right? So the idea here is that if DI is randomly assigned, that's when strong ignorability is satisfied. If you were trying to be clear with somebody who really, somebody who hadn't taken this class, or somebody who got their PhD 30 years ago and didn't follow this sort of thing, you might say that's exogenous as well. But conceptually, this is kind of the key definition we'll need for this. And under that condition, that's going to basically get us identification. So why would we need this condition? So intuitively, I think almost everyone here probably understands why you can't always estimate a treatment effect, right? So imagine there's some unobservable variable, UI, which is binary, for example, where they're not independent from one another. So basically, the idea is, this is kind of related to my example that I just gave, where I was saying, say I don't give the treatment to Natalia because I think she's going to have a bad outcome. Well, if that's the case, then what I've done now is there's some variable such that the person who has UI equal to 1, well, they're more likely to get the treatment, but they're also more likely to have a higher treatment effect than vice versa. The person who had UI equal to 0 and UI equal to similar for UI equal to 0, that they're going to have a lower treatment effect. So what this is doing is influencing the treatment assignment and a predictor of, it confounds the treatment effect. So any time then, if we tried to estimate the treatment effect using this random, basically this sample, this yi0, yi1, and di, if we just use the yi and di, then what we have is selection bias. So if we estimated the effect of, if we tried to estimate this parameter, say the average treatment effect here, and we plugged in for these terms and we just use the observed data, then what we would get is we would have it such that it would be biased upwards, because we would have given more of the treatment to the people who have a positive effect and less of the treatment to the people who have who would have a lower effect. So this will be basically, a lot of this course is going to be centered around trying to address this issue. Conceptually, you can see this here, is that when DI is strongly ignorable, conditional on X, then the treatment effect, this average treatment effect, is equal to, and then we're summing up over the XI. This is just to, if you don't need to condition on anything, if XI is just a constant, or if it's basically strongly ignorable, it's a random assignment, then just ignore the XIs. But what we can do to estimate the treatment effect is we just take the observed outcome, conditional on the treatment effect, the treatment being on, minus the observed outcome where the treatment effect, or the treatment is 0. We're just taking the treatment group, the control group, take the difference. Basically, this all comes from the fact that, remember that this expectation of yi 0, well, that's the same thing as the expectation of yi 0 conditional on di equals 0. And then we just plug in with how we know yi0 is defined. Remember, yi is defined as a function of di equals 0, or excuse me, di times yi1 plus 1 minus di yi0. If we plug these in, then what we can get to is something where we observe in the data. So I'm gonna sit on this for a second, because I know this is, I didn't write it out in the slides, but I want this to be clear because this is important. So let me make sure you guys can see this. Can everybody see my board for a second? Let me pin this spotlight for everyone. So conceptually, the pieces that matter Can everybody hear? I'm like booming right now. Can you guys hear me okay? All right. So remember that this is our definition for the Reuben causal model. And then, so the point is, well, if we do this, this is the thing that we were trying to estimate, or one piece of what we were trying to estimate. Well, we know this is true based on strong ignorability. Basically, this expectation is equal to this because these guys are independent from one another. And then you just say, all right, well, let me just rewrite and kind of plug in for this, right? yi0 is just equal to yi1 when di equals 0. Sorry, when di equals 0. So then I'll just plug in. And you're basically done. This is an empirical analog. We actually know what this y, we observe this yi. And so these pieces kind of map together and we're done. So the two things together, both the definition of the definition from the Reuben causal model plus strong ignorability get us that term. Any questions on that? Okay, great. All right, I'll go back to sharing my screen. So this is pretty awesome in the sense that the strong ignorability concept has given us a way to generate counterfactuals using averages. But as we'll see kind of over the course of this class, this is kind of the punchline for everything. Everything is going to be trying to use something to figure out what the counterfactual outcome is. So what's this intuit? So like just to hammer this point home, we can estimate expectational yi for the treatment is equal to 0.75. So here's some data here. So we have 8 people. We can take the conditional expectation for these guys for the treated, that's 0.75. And then for the untreated, for the control group, it's 0.25, right? And so we've gotten that here because there's 3 who are treated. These guys who are treated, the expectation is 0.75. For those who are untreated, it's 0.25. Basically what we've done is we've defined our counterfactuals for each of these guys to be 0.25 or 0.75 respectively. If we had covariates, we could condition in those groups. And what that would eventually basically will show is that this is going to give it, we're going to talk about this on Thursday, is that this is going to give us an unbiased estimate of these underlying average treatment effects. This is identified because of this ignorability condition. This is all non-parametric as well. We haven't made any model restrictions on the data generating process. The only thing that we need to restrict is this idea that the treatment is randomly assigned. Not randomly assigned, but is strictly ignorable. So random assignment is a kind of much stronger assumption, right? I mean, that makes sense to some extent. Like this, they're observationally similar in this, but more importantly is that they're strongly ignorable. Okay, assume no questions. All right. Okay. Oh, we're doing great on time. Might even end early. Who knows? All right. So let's talk now about how many people here actually here. Do I have? Oh, I have to set it up. Okay. Oh no, so much work. Hold on. This is my MBA teaching spilling in. All right. Poll time. Have you ever seen a directed acyclic graph? And by seeing, I kind of mean more than like you've seen it in something and didn't understand, but you've actually worked with it. All right. 4 people are working on their emails. 3 people are. 2. All right. Okay. So I'd say the vast majority of you haven't. This is relatively uncommon in econ. I think it's much more common in a lot of other social sciences. Feel free to jump in if there's kind of things. This is relatively new to me, but I think this is quite powerful to think about these different ways of doing this, and I want to kind of encourage you to do this. If you're interested in this, I definitely would go and look some more at the Cunningham textbook has a whole chapter kind of devoted to this topic. I'm going to kind of talk about some simple examples, but he goes into a lot more detail on some of the examples. A good thing to kind of keep in mind about this topic before we kind of jump in, and I'll revisit this, is that this is going to be a good example of something that's really helpful for clarifying some ideas. But if for the economists in the audience, if you want to use this, you are going to face some additional fixed costs in explaining this. Hopefully that makes sense. It's more or less like, if you go to your advisor and you're like, here, let me draw you the DAG of what my research design is, half of them are going to say, I have no idea what you're talking about. So there's kind of this key point that this is valuable sort of terminology and technique to potentially use, but you're going to need to spend some extra time translating or figuring out exactly how you want to frame what's going on. So with that in mind, let's jump into it and kind of talk about what can be useful here. What we did above was we were encoding random variables relationships basically through functions. More or less, we were defining them through potential outcomes and defining statistical relationships between the two. There is an alternative approach, this DAG's approach, which is doing this graphically. Now, it has some similar modeling under the hood in the sense that the relationship between these variables can be written with functional forms. This is what this structural equation modeling does inherently. But you can actually do almost all of this using graph notation, and it can be very powerful. And the way that it works is you encode the causal relationship between D and Y using an arrow in a graph. And the direction of the arrow basically emphasizes that D causes Y and not vice versa. So what's challenging in this notation is that simultaneity is really hard to encode. So if you're interested in, for example, thinking about equilibria, you'd have to do a lot more thinking about the time dimension. It's severely lacking in some of these things, but it is quite intuitive in a number of ways. So, thinking about the effect of D on Y, drawing that down, you're like, okay, D causes Y. That doesn't seem deeply challenging. The idea being here that if I change D, I change Y, right? That's pretty intuitive. What it also lets you do is talk about this problem that we were talking about for identification, right? So there is this problem here where there was this problem here where we were thinking about this unobservable U, right? So I made this point like, oh, this is going to create serious issues for estimating this effect. It won't be identified because maybe Natalia is getting sort of treated for the wrong, like in the sense that it's not random assignment. That's going to cause identification concerns in the potential outcome framework, and it's going to do the same here. So in this terminology under DAGs, this U here, where I've put a little dashed box around it to indicate that it's unobserved, is a confounder, right? So that's like something you would use in your econometrics class, right? When we talk about running a regression where we have an omitted variable bias, that would be confounding. It would have run a confounded regression. And what's great about this notation is the idea that we can examine, we can basically talk about the different paths in which D is linked to Y. So now, and this is what we're going to do in a number of these settings, we can look at the standard direct effect of D on Y. So that's the one we were doing before. That's the one we're interested in, where all of the arrows are going in the same direction. So D is affecting Y and it's sort of causal direct effect. Then This is one of what's called the backdoor paths. So what does that mean? Well, there's a path. It's obviously not directed in the right way, but there's a path that goes from D to U to Y. And this backdoor path isn't causal, right? It's not that D causes U and then U causes Y and that there's multiple channels. It's really that, well, U causes both of them, but we can draw a path from one to the other. The key point, and what we'll get more into sort of what exactly defines this, is that because there's two backdoor paths, or because there's a backdoor path in addition to the direct path that we're interested in, the effect of D on Y is not identified. So basically, I'm not going to show you the formal results for this. I'll link kind of the sites if you're interested in of doing this. The notation setup is frankly a lot for kind of proving when something is D-separated and not. But the idea is that when there is a backdoor path, in addition to the direct effect, if you're not able to block that backdoor path, then the effect of D on Y isn't identified. And that is exactly the story that we were just doing with potential outcomes. It's the idea that, look, the problem is that U affects both Y and R affects the choice of D. And so then there's this contamination in thinking about our counterfactuals. What's nice is that we can now start thinking about, all right, well, let's say we replace U now with something observable. So this should say an observable X in the identification concerns above. So we've taken U and now we have X, which is observable. So X is still confounding, right? If I run a regression of D on Y, like in the potential outcome frameworks, or if I ignored the effect, if I didn't condition on X, my random assignment would have potentially been confounded. Same idea. There's two paths. Potentially we have these this contaminating effect through X. What you can do when something is observable is you're able to condition on the variable to block it. So the basically notational thing to understand is that if you condition on X, a confounder path is blocked. So you basically take any path, you condition on one intermediate variable in the middle, that blocks the path. And now there's only one path that we're interested in, which is the direct effect of D on Y. And that's just exactly the same thing that we did in the previous setup, right? I mean, this is why I'm saying that these things are multimodal in the sense that when we did average treatment effects and we were thinking about this in the potential outcomes framework, the idea was to say, all right, well, what we need is strong ignorability conditional on X. If that's true, then we can estimate the average treatment effect. We would just do it for every X. We would estimate the effect and then we would average it up. That's very nice. And that sort of maps one-to-one. One thing that is, I think, much more powerful in this setting is that DAGs really do an excellent job of formalizing this concept of a collider. And this is something that potential outcome frameworks and economists more generally struggle with in a lot of settings. So we're going to take a bunch of time on this. I know it looks like, well, not a bunch of time. We're going to take some time on this to make sure that we understand this, because this is really, if you want to understand the kind of the value of DAGs, this is one of the big ones. So consider this following example. Now, what have we done? We've said, okay, D affects Y still, but now instead of X affecting D and Y, it's that D affects X directly, but it also affects it through Y. We still have the same backdoor path problem in the sense that D goes to X and then X goes to Y, and we have the direct effect. Well, the key difference here in this, basically this literature, this literature basically, the point is that a backdoor collider is automatically blocked. So formally, what this means is that when a path is such that there's an intermediate variable where basically the two causal arrows hit one another, then that path no longer generates bias. So here, if you just run the regression of D on Y, you'll estimate the effect. So let's think about why that is, right? So I've told you this, but intuitively, hopefully this should make a lot of sense. Imagine now I told you that let's think about the right example for this. Imagine we did the following. So this is coming back again to like a education example. So say we take the following question: what is the effect of college education on two things? One, someone's income and someone's occupation. So for simplicity's sake, D can be whether or not someone gets a college education. Y can be this question of what occupation you choose. And then X can be what your income is. Now, we could quibble about whether or not this is a good diagram for this. But in this setting, you could believe that, well, what college education is going to do is it's going to affect both the occupation I'm going to choose and my income. And the occupation has an impact on income as well. If you're just interested in the effect of college education on occupation, what this diagram will tell you is that conditioning on income is going to bias the impact of education on occupation. And that makes sense, right? Basically, if I say, well, what I'm going to do is I'm going to condition on making $100,000 and then compare what the effect is of college education on what type of occupation you choose. You're already going to be conditioning at something that is basically a post-treatment variable. You're subsetting in a weird way based on unobservables on who gets into what setting. So another kind of the more famous example of what a collider is which I always find a little bit weird, but think about looks and comedic talent. So people always talk about it's like, oh, well, movie stars, like they basically, there's always this trade-off between, you either have to be really attractive or they have to be very funny. And it's like, well, what you're doing, actually, this is a bad example. It is a collider, but it doesn't fit with the DAG that I just drew. Conceptually, in that setting, if you condition on movie stars, what you've done already is subset on a certain type of individual. And so then you capture this negative relationship between looks and comedic talent, for example. Whereas if we look unconditionally in the population, that relationship obviously disappears. Conceptually, more generally, from basically a terminology standpoint, when you condition on X, so we have this backdoor path here, the effect of D on Y, it's blocked when there is a collider. But if you condition on X, you open the backdoor path. And so what we want conceptually is to avoid conditioning on colliders or upstream variables from this. So another thing that is affected by this. But we want to condition on the things that are confounders. So basically the idea is identifying colliders and identifying confounders is kind of a crucial aspect on identifying whether or not an effect is identified. The key value for a DAG is basically laying out a model of causality and clarifying which effects need to be restricted even in a complicated setting. So for example, how is the effect of D on Y identified here? Or is it identified? So we take a look at this for a second. So we have four variables for now, right? So what we could do is we say, all right, well, there's a direct path of D on Y. We'll just do this here and then we'll go up to the board. There is X. So there's a path between D and Y, which is D to X, a backdoor path, which is D to X to Y. And then there's another backdoor path, which is D to Z to Y. But X, remember here, is a collider and Z is a confounder, right? So in this case, how would we identify it? Well, because this is a collider, we don't want a condition on X, but we do want a condition on Z. So we condition on Z, we estimate the effect of D on Y, and that would this would block this path, and we would just have this effect identified. In this setting, could we do it? So I'm cheating here. This is not something we would know exactly how to identify, but let's walk through it. Let's talk about what the paths are. So there's a direct path from D to Y. Then there's one backdoor path, right? Which is D to U to Y, where U is a confounder, right? It's an unobservable that's affecting both. The question, of course, is this identifiable? Z has no impact because it's just upstream from us. Effectively, under this setting, from what we've talked about so far, this is not identified. We can't identify the effect of D on Y. Can anyone think of, in this setting, what does this look like? Does this look like anything in particular? For those who are kind of familiar with the econometrics, does this look like a particular setup to you?
Is it just like the instrumental variable setting?
Yeah, exactly. So this is, I cheated by calling it Z so that to give a setting, but that's exactly right, Get. So Z, we can identify the effect of Z on Y, right? So Z, we see the path. There's a direct causal path from Z to Y. That's no problem. There's nothing backdoor. It's exogenous. Everything holds. Same thing, we can identify the effect of Z on D. What is the question, and the million-dollar question, is can we use those two pieces to identify the effect of D on Y? And so later when we talk about IV, that's what is going to be here. But kind of the key point, just as to highlight this, is under this setting, under purely unrestricted heterogeneous effects, so we haven't put any restrictions on the types of effects, it's not identified right now. So if you've seen IV, for example, you know that like under heterogeneous treatment effects, you need something like monotonicity to hold, for example. And so in this setting, we wouldn't be able to identify it. Any questions about that so far? Okay, kind of in summary about this, what are the key steps with the DAG? So step one, write down the DAG, identify what effects you want. Step two, write all paths between the two nodes, basically causal or not. You want to identify what are the direct causal paths, e.g. the arrows that all flow in the right direction. So that's like, in some ways it feels like it's a game. And so people who work on this topic love this aspect of it. You just have, it's an algorithm in which you set up these pieces. So let's identify what are the direct causal paths that we're interested in. And then the question is how many backdoor paths are there, and are they blocked, and can you block them? The key point that I think is extremely valuable and that we don't do enough to talk about is conditioning on colliders will cause more harm than good. So I really want to emphasize this, especially for those folks. I don't know if there are any, I know that at least a few people who do stuff on corporate finance and other settings. Conditioning on stuff is not always a good thing. You don't always want to be like, all right, I'm going to throw in a bunch of variables and look, now things still work. Really what you want to be thinking about is what is the things I need to condition on, e.g. uses controls, to estimate the effect that I'm interested in. And that's a very crucial distinction. And I think it's something that is really sort of an important distinction to keep in mind when you do your empirical work. This DAG thing, I'm going to try and come back to it in different settings. I think especially in IV, it's very powerful. I am not an expert in it, so I'm certainly not going to use it in a huge number of settings, especially for those of you who know how it works and have used it in other settings. Please do feel free to kind of raise your hand or mention it if it's something that you want to talk about, because I am interested in kind of emphasizing this point. Okay. As we this is kind of we're actually going to end a little early. So let me kind of conclude by talking about thinking about structural equations and causal effects. So Phil Hale has these really kind of amazing slides that are on the course website that you should look through, because it's kind of an amazing rant. I don't know if has anyone taken this class with Phil? Like, this is from a class he did last year. I don't know if anyone did this. No? Okay, well, I'm going to do my best. Please don't report back to Phil that I butchered his takeaway from this. But what I really think can be dangerous in this is, the vast majority of you in this class are economists or thinking about economic questions and sort of have a underlying structural model of how things work. And when we started at the top of the hour, what we talked about was the idea that, estimates that inform our economic model, we have a causal model in mind, even when we're not doing causal estimates. And so what I mean by that is that you should have even if you write something down that you call reduced form, a reduced form equation is something that is implied by a structural model. So this is Phil's kind of like first huge pet peeve, which is to say, when I write down something that says, the effect of X on Y, I run a linear regression and I'm like, well, this is the reduced form effect of X on Y. That implicitly is already putting a huge amount of assumptions about the structure of whatever causal quantity we have in mind. This shows up especially if you do stuff related to market choices. So in health, for example, if you're thinking about plan choice and you start thinking about, well, what is the impact of some exogenous variable on the outcome? Well, you have to then start making really specific choices about the interaction of choices across, of errors across different choice problems. So when you think about the reduced form, really what you're saying is that there's an exogenous variables. So in our potential outcome framework, we were talking about DI being some treatment. And there are unobservable structural errors that are in there. And the outputs should be endogenous variables, things that we care about. And we're interested in manipulating our treatment variables or our exogenous variables and understanding how those things respond. Those are useful because we want to be able to talk about counterfactuals, right? We want to be able to say, all right, I use an experiment that creates variation in pricing for a plan. That shows me how much people are responsive to this pricing. By using that variation, I can plug that into a model, and that tells me some kind of counterfactual that if I increase the prices for everyone by X amount, what would the effect be? All of these settings, and this is kind of, so I'm not digging too much into this because we would have to do a lot to kind of set up what the different models are, and it's also not my expertise, but this is kind of the third of the multimodal. So we talked about potential outcomes first. Then we talk about DAGs. Now we're talking about kind of thinking more generally about structural equations and causal effects. And all of these are different ways of trying to think about how can I talk about a counterfactual setting for my outcomes. And so the potential outcomes framework, basically the key insight there was that for every individual or every unit, we can think about there being counterfactuals. So, the idea that there's missing data between the two of them, that was kind of the key insight for Ruben's setting for doing this. But this isn't magic, right? There are ways of reframing that notation into, what looks more like structural econometrics. This is, potential outcomes the idea of thinking about this as counterfactuals was not kind of brand new. Econometricians have been thinking about this for a long time. And so the thing I want to leave you with is conceptually, think about this potential outcome framework that we did here. So this is, yi is di times yi1 plus 1 minus di times yi0, right? Well, in this notation, we could just strictly rewrite this as, okay, well, yi is some constant plus di times tau, or tau is the average treatment effect, plus there's heterogeneity. So consider this to be like a random variation in the effect of di on yi plus some structural error term. So how would we do that? Right? So how do we write that down? Well, if we do this here, right? So if we take this one and we take this setting, well, what we get is that first what we can do is we can say, all right, well, we could just rewrite this as yi0 plus, and then we'd have yi1 minus yi0 di, right? It's like times di. This is just notationally rewriting this. Oh, I should pin myself, sorry. I guess I am screaming, so it's probably. So in this setting, this is now, I'm thinking about this constant plus the treatment effect. Well, I can then redefine this in terms of some average effect. So I could say like, oh, well, there's the average impact on those who are untreated plus, you know, this error term. And we could call this alpha, right? So it's like this should be like a control mean. And then we have the deviation of that from it. So this is, you know, notationally, I call this UI. So now what we have here is we have alpha plus UI. And then we can just rewrite this in terms of, well, there's a DI times some tau that I'm interested in, plus some VI. And the VI, obviously, is going to be the tau I minus tau, where tau is kind of the average treatment effect, right? It's how much I deviate from the average treatment effect. Okay, well, so notationally, that's fine. I've just put different letters on it. But if you think about what this is doing, think about your econometrics class, either undergraduate or not. In this setting, now all I have to do is think about, I'm running a regression of DI on YI. Well, when is DI going to capture tau? It's going to be when the error terms are uncorrelated with DI, right? Well, so what are the error terms? The error terms are UI and VI, where UI is, those two pieces are basically the distribution of the potential outcomes. So what that means to say is that if we think about these underlying pieces, that if we have strict ignorability, well, then this regression is exactly going to estimate tau, and we're done. So, okay, why do I care about that? The reason I'm emphasizing this point is I think what is quite common, oh, wrong camera, sorry. What tends to happen is that there's a lot of siloing of thinking about these methods. So conceptually, you know, there's a potential outcome framework. There's, I think, a more strict school of econometric theory that is doing stuff more with structural equations like the alpha and everything else. And I mean, sort of this DAG one is kind of even more separated. Conceptually, what I want you to understand is that these are all pieces that are thinking about a similar problem, namely these joint statistical distributions and how we can estimate counterfactuals. And a lot of the notation I'm going to use is either going to be in the econometric school or in this potential outcomes framework when I can. But you just want to keep in mind that these are all ways of thinking about the same underlying structural problems.